Question 70 is like a vast but shallow lake. It occupies a large area but contains very little. There are only 3 variables given, and all 3 must be used to solve it. The difficulty lies in knowing the necessary technical terminology and how the properties of a refrigerant change through a mechanical refrigeration cycle. These are broad, expansive topics, having only a little analytical depth. Initial critical thought solution elements. 1. What are you solving for? The mass flow of a refrigerant as it travels through a refrigeration cycle. 2. What is the fundamental process? Energy flowing through a refrigerant, and what is called the refrigeration effect. 3. What are the first considerations to find the solution in connection to the fundamental process? Appropriately placing a mechanical refrigeration process on a pressure enthalpy diagram. 4. Are there key assumptions? Ideal suction and discharge pipes, and ideal efficiency of the compressor. There are 2 equally legitimate paths to a solution for this problem. One path takes you through reference material to a chart, where the solution is looked up. The other takes you through unit analysis to a very simple equation. Both require some fundamental knowledge of the pH diagram, the mechanical refrigeration cycle, and finally, how the 2 fit together. Starting with a pH diagram, here are the following things you must know upon entering the PE. 1. Here is the saturation dome. This is the location where the refrigerant changes phase, but not temperature as it gains or loses enthalpy. Notice, the problem states saturated conditions. 2. Here is the saturation line. It's split into 2. The extreme left is saturated liquid. The extreme right is saturated vapor. 3. Here is the subcooling region. This is where there is a change in temperature as the refrigerant gains or loses enthalpy. Notice, the problem mentions subcooling. 4. Here is the superheated region. Again, this is where there is a change in temperature as the refrigerant gains or loses enthalpy. A typical refrigeration cycle will take place in the saturation dome and in the superheated region. Unless a problem explicitly states it, assume nothing happens in the subcooling region. As a refrigerant flows around a refrigeration cycle, it experiences changes, most obviously changes in pressure and changes in enthalpy. These lines indicate a path where the refrigerant changes conditions as it flows through a refrigeration cycle. This general shape can be considered standard, but it can vary, like in multi-stage refrigeration cycles. If no other information is given in a question, assume this general setup. Each segment of the shape is associated with a mechanical component in the refrigeration cycle. This demonstrates the operation of the evaporator. When exposing the saturated refrigerant to the air it must cool, the refrigerant pulls that air's heat energy into the refrigeration cycle. This causes the refrigerant to increase in enthalpy, and in doing so, to vaporize, but not to increase in temperature. Once the saturated refrigerant becomes completely vaporized, the work of the compressor is shown here. Pressure is added to the saturated vapor, which takes it out of the saturated condition and makes it superheated. Now it increases in temperature. This increase in temperature is only a byproduct of the purpose of the compressor. The purpose is to add pressure to the refrigerant to make it condense easily at higher temperatures. The change in temperature of the refrigerant in this section has nothing directly to do with the act of refrigerating. It's just an inevitable consequence of compressing. This issue is critical to understand because it identifies what is called the refrigeration effect. Speaking in general terms, the ability to refrigerate is shown only by the change in enthalpy within the saturation dome, here. What happens out here, in the superheated region, doesn't do any refrigerating. It's not included in the refrigeration effect. The real stuff of refrigeration happens here, which is the change in heat energy between saturated liquid and saturated vapor. Here is the refrigeration effect, a pure delta H. Here is the work of compression, a mix of intentional delta P and incidental delta H. The refrigeration effect is used to determine the capacity of a refrigeration cycle, but there's more to it than just that. Capacity depends on the flow of the refrigerant, and flow depends on the suction and almost pump-like work of the compressor. So, the refrigeration produced by the cycle is generally considered refrigeration produced by the compressor. Notice that the question says the compressor produces 49.5 tons of refrigeration. You should understand this context when talking about compressors producing refrigeration, and not compression. Continuing along the shape, this represents the action of the condenser. Here, the refrigeration cycle rejects the enthalpy taken in earlier by the evaporator. Unless specifically indicated in a question, always assume this terminates at the saturated liquid line. This is what the question means when it says, no condenser subcooling. Finally, this represents the action of the expansion valve, which obviously decreases the pressure of the refrigerant. This section matters the least to the solution for this question. As given by the problem, the compressor sucks in saturated vapor refrigerant at this point, 25 degrees. It discharges at this point, 173 psia. No condenser subcooling means that the refrigerant is taken to this saturated liquid point, 115 degrees. As discussed earlier, it's between these 2 points that you see the capacity of the compressor, except for one thing. Notice no time values exist for any of this data. A refrigeration cycle operates in time as it moves the refrigerant around the circuit. Capacity must capture the element of time. You will find it in the units, tons of refrigeration, as given in the problem. You should already know, tons of refrigeration has a time element, which can be communicated in its conversion to BTU per hour. Now, with the variables, terms, and refrigeration concepts clearly identified, the 2 solution paths can be given. Beginning with the chart lookup option. Notice in the NCEES practice test, this is called the alternate solution, and it references the ASHRAE. You won't have the ASHRAE in the PE exam. You'll only have the NCEES Mechanical Reference Handbook. In version 1.1, you'll find the appropriate chart in section 8.7.2. The refrigerant leaves the evaporator here, the exact place the compressor begins. Notice this evaporator line shows a constant temperature of 25 degrees. No beginning to end changes in temperature. So, 25 degrees is the temperature of the refrigerant inside the evaporator. The temperature of the refrigerant sent to the evaporator is found at the end of the condenser section here, 115 degrees. A quick note, in the NCEES practice test solution, there is a pH diagram which identifies this point at 104 degrees. This is a typo. The point really is 115 degrees. So, on the chart in section 8.7.2 of the NCEES Mechanical Reference Handbook, find the 115 degree line labeled Liquid Temperature to Evaporator Feed. Where this intersects with the x-axis value of 25 degrees, find the value of roughly 3.55 on the y-axis. The y-axis label indicates 3.55 must be multiplied by the tons of refrigeration to give the operational flow rate. 3.55 times 49.5 tons of refrigeration equals 175.7 pounds per minute. The second solution path focuses on unit analysis and saves you from searching through reference texts. It uses critical thought based on the concepts shown earlier. You must solve for a mass flow rate in pounds per minute. You're given an energy flow rate of 49.5 tons. A ton is easily converted to BTU per hour by multiplying it by 12,000. Memorize this conversion. You're going to need it. To move from BTU per hour to pounds per minute, you'll need 2 units. 1, a simple time conversion from hours to minutes. And 2, a value with a unit of BTUs per pound. What is BTU per pound? You should know that automatically. It's enthalpy. You have the 2 points on the pH chart showing the refrigeration effect within the saturation dome. Between those two, there is a delta H, which is the value in the units needed. 106 and 50. The delta is 56. Now, convert and cancel out. The solution is 176.8 pounds per minute. To get good at questions like this, study ASHRAE HVAC Systems and Equipment, Chapter 38, Compressors, Section 1.1, especially Figure 4 and Equations 3 and 4. In the ExOverZero practice tests, do problems Test 1, number 68, Test 2, number 69, Test 3, number 79, Test 4, number 67.